think we're going to go ahead and get started here. Seems like people are coming in. I'll give my intro. Hello, everyone, and welcome to today's webinar hosted by Photonics Media. My name is Corey Dolbashian, a photonics product line support expert here at Thorlabs, and it is my pleasure to moderate today's talk, which will be given by my colleague Carol. Carol is a science and technology enthusiast who has been with Thorlabs since an acquisition back in 2020. She is currently working as the subject matter expert for Thorlabs' Vantage Pro galvanometer product line, regularly assisting customers with choosing catalog products, designing non-standard configurations for projects with specialty requirements, and guiding integration of said systems into new or existing experimental configurations. Throughout Carol's talk, please feel free to submit any questions you have using the Q&A tool. I will be monitoring your inquiries throughout the presentation, and at the end of the talk, we will address as many of these questions as we can in the time limit. Now, without any further delay, I would like to pass the proverbial microphone over to my colleague Carol here.
Hi, Dr. Dolbashian, and thank you for the kind introduction. And thank you to everyone who has joined me today to talk about beam steering. When I get asked what I do for a living, my response of I'm in manufacturing has the inevitable follow-up question of, oh, what do you make? And I have learned that there is no reply that I can give that does not lead to either additional questions or just a blank, somewhat vacant look. Because of this, I'm also grateful to the team at Photonics Media for their efforts to make information like this more accessible to a wider audience and through this webinar series. So thank you also to our gracious hosts for holding events like this for us to learn together. So where to start? I'm not an author of children's books, so I can't rely on the classic beginnings of Once Upon a Time or Long, Long Ago in a Laboratory Far, Far Away. So instead, we're going to begin with you and your application goals. Let's consider them a little bit. The first thing that I like to determine when talking about any product choice is what the main area of concern is going to be. Do you need a fast system or one that can handle an exceptionally high powered laser or a tightly focused spot on the work surface? There's usually something that is going to be of critical importance above other considerations that might be in the system. And I like to identify that right out at the start. There is no such thing as a standard Galvos system for any given application. But listed here on the screen, you'll see there's a couple of general application categories that we encounter frequently in the imaging space, and what I would consider to be the more frequently requested features that I get for each of those applications. The microscopy applications are well known for requiring high scanning speeds that allows them to attain better contrast, greater resolution and sensitivity, and to just minimize data acquisition time. This requirement for fast scanning, along with lower laser powers, typically means that applications of this nature are more likely to call for smaller mirrors, such as the one that you can see here on the QG4X Galvo. This Galvo that was used, this is the Galvo that was used in an XY pair by our imaging team to collect the convallaria image that you see on this slide and that you might have seen when you registered to attend this webinar. So that's their work. And counter to the microscopy applications, while still being comfortably within the imaging family, the LiDAR applications are more likely to call for larger mirrors that can gather a greater volume of light as it re-enters the system, not just on the way out. And that's done via systems such as this QS45 that's shown next to the QG4 in this picture. These two systems side by side are to scale in this photo, and looking at them, it does not require a significant amount of imagination to understand that the smaller system can just move faster. And if at this point you're sitting on the other side of your internet connection, yelling at your screen, my microscopy application doesn't call for that at all, please call me. As Corey mentioned in the introduction, I am a general science enthusiast, so I would love to hear what cool thing it is that you're doing with microscopy that calls for somewhat of an unusual configuration, or what I would consider to be an unusual configuration. So call me. When I was originally planning this presentation, I had intended to cover two application families on this side, the imaging family that we have here, and the second was going to be the laser processing of materials applications. But then when I was adding that second family, it spiraled very quickly to its own slide. So let's talk about laser processing for just a moment. In microscopy and LiDAR, it's a bit easier to generalize the requirements, but applications that fall underneath this wide umbrella of the term laser processing of materials are so varied that it is even more important to consider what the individual priorities of each integration are going to be. The key here is the variation in the materials that are being processed. It makes choosing the right system a little bit more critical for these sorts of applications. Some materials process more quickly and so can use smaller, faster components to increase system throughput. However, a smaller mirror that can be scanned at an ultra fast rate will be of no use to you if the scanning speed exceeds the ability of the laser to process the material. You may be over here saying, okay, we'll just increase the laser power. But then if you do that, is your small diameter laser beam with your high powered laser going to damage the optics of your system? Spoiler alert, it will. Stay tuned. Those pictures are coming up on the next slide. Fantastic damage. But before we skip ahead to the destruction, other potential priorities that can affect the galvo that you choose are factors such as the required focused spot size or the size of the processing field. Both of these parameters are going to be also heavily determined by the focusing objective that's chosen, whether that's an F theta lens or another type of focusing optics. And we need to think of these systems in a whole holistic fashion, the entire system working together, not just as the individual parts. And so figuring out what those priorities are and being able to make adjustments to really compensate for differences and end up in a position where the system does have the overall performance that you want, very important. So as promised, fantastic destruction. These two images demonstrate the importance of the two principles that we're going to talk about here much better than, frankly, an hour of me talking about the subject ever could. So this picture on the top is a prime example of how it is not just about overall beam wattage, but it is about beam density. So the relationship of that power to the diameter of the laser beam. In this particular case, this was a beam that was roughly half the diameter that it was supposed to be. And had it been fully expanded, the mirror would have performed adequately, but it wasn't, and the optic suffered immensely, as you can see. And the second principle is not just the power or the energy that's going onto the system with the density, but also the wavelength of the laser, and being certain that the light source is suitably paired with the reflectivity of the optic. So how reflective is the optic at your chosen wavelength? And this lower picture demonstrates what can happen if your chosen optic is not suitably reflective at the wavelength you are using. While no optic is going to be 100% reflective, it is important to remember that any non-reflected energy is going to be absorbed as heat. And with sufficient energy and insufficient reflectivity, the delicate optical coating or the substrate can be damaged as you see in this picture. Spend some time thinking about your laser power or your energy if it's a pulse laser and your beam diameter. There are plenty of online calculators. You don't even have to do this math by yourself, but make sure that the optics that you choose are a good match with your light source, or possibly my next presentation will include a picture of your handiwork. You know who you are. Moving on, if we are thinking of this whole process as individual steps of selection, by now we know roughly what size motor and mirror we're going to need, as well as the coating that's going to be on that mirror. So we're going to change gears a little bit from the basic function of the system and its components and look more at the form that you're going to need. All scanners are going to require some level of integration. The questions that you have to ask yourself are, how much do you want to do of that integration? And what level of that integration are you willing to take on, or are you looking to take on? This is all about finding the balance between ease of integration and the flexibility that may be required. Some of the questions you may want to ask yourself are, what space is this integrating into? Is this going in a machine that has an established envelope that you have to stay within? Or is it going on an optical table that will have more room to be flexible? An established envelope may require individual galvos to fit in the space constraints that already exist, while a two-axis open frame system is going to be more flexible than a packaged solution on a benchtop. But then you also need to consider, are there environmental concerns that need to be accounted for? Is this going into a sterile lab environment? If so, that's great. But even in a sterile lab environment, is there going to be the opportunity for contaminants from elsewhere in your process to end up on the mirrors, which can happen in even the cleanest of labs? We see this in some of our bio applications that have like a splashback from the work surface that can result in contaminants being deposited on the mirrors. And then even if there is a 0% chance for contamination from your process, do you have a concern about accessibility in a shared lab space? We have seen a lot of systems come back with fingerprints on mirrors that didn't necessarily come from the person who regularly uses the system, but maybe from a lab mate. And if you're not in a lab, so you're out of this sterile lab environment entirely, is this going to be installed in a space where there is going to be the possibility of dust or debris, oil, or other contaminants being in the air? And will it need to be sealed against the surrounding environment? If it does need to be sealed, how sealed does it need to be? A negative pressure system is a bit easier to install with a packaged solution. But if you want something with a super industrial sealing, an open frame solution that you can build into a box of your own design may be easier for you to integrate into your system. The highly configurable nature of these systems means that we can likely get you a footprint that meets your needs, either enclosed or open frame, that will use the galvos that you're looking for, even if that configuration isn't one that's currently listed on our website. We might have it on the secret menu. And many of the secret menu items also still have very short lead times because they're configurations that are non-standard, but that are built out of standard products that we still have on the shelf. So now, for anyone who's still keeping track, at this point we've picked the motors, we've picked the mirrors, the envelope that we're going to build them into, and we're going to move even further away from the motors, and we're going to talk not just about the form, but we are going to talk about controls. There are two basic control signal types, analog and digital. I suppose technically these days there's a third one if you talk to the folks that populate the quantum computing realm, but that is not the topic of this webinar, and we don't have that type of time today. So let's just keep moving, analog and digital, two types. In either case, you will need a piece of hardware that is going to generate the command signals that you will send to the Galvos system. I'm going to start with analog and the basic outline of how analog Galvo command functions. The hardware that's used in this case is typically something like a waveform generator or a DAC. The hardware will generate the analog voltage that's then passed to the servo amplifiers. And the servo amplifier will have a scale factor for the commands that will take this voltage and then translate it into the angle of deflection that gets sent to the motor. DACs are great. They are easily programmable using a variety of lab tools and accessible software packages that are readily available from a diverse supply of vendors. The accessibility of these controllers makes analog commands an attractive choice for anyone looking to perform basic movements, regular patterns, such as the raster scan that you can see demonstrated here on the far left of this image, or the bidirectional scan that's in the middle, but also simple geometries, circles, diamonds, squares, things of that nature. Analog is also excellent for step and settle type of motions. Because of these characteristics, these types of controls, analog, are common in the imaging applications like the ones that I mentioned previously, microscopy and LiDAR. And if you're thinking that this control method would be one that would be right for your application, I would strongly urge you, before you sit down with a credit card and place an order for equipment, to take a look at the capabilities of your command generator prior to purchasing the Galvos system, or prior to purchasing the command generator if you already have the Galvos system. Particularly when it comes to the output voltage range of a DAC. Waveform generators, it's generally adjustable, but some DACs output commands in the range of 0 to 10 volts, some in the range of 0 to 5 volts, and it's important to know which one you have and that it matches appropriately with your Galvos system so that your equipment does work in the anticipated way. Digital controls are a little bit more complicated than their analog counterparts. So instead of a simple analog voltage that results in a deflection angle, this method uses an industry standard command protocol called XY2100 that's been around for longer than me. The hardware required by this method is a control card that is capable of generating the XY2100 signals, along with a software package that has a UI where individual jobs can be designed and the precision timing of all components in the system can be coordinated. This snapshot above is from the UI that we sell here at Thorlabs. We call it Wave Runner. And you can see our dog, which was actually used to mark the image that was a couple of slides back. The control card is typically built into some sort of a packaged system controller that functions as the central hub to which all other system components are attached. The other components are the laser, obviously, need one of those. Any motion control devices, so things like rotary stages or translation stages, safety interlocks, shutters, you get the idea. Digital XY2100 controllers are fantastic for complex jobs, arbitrary vectors, random characters, things of that nature. These are more often than not jobs that fall into that laser processing of materials family. So these are your laser marking, welding, additive manufacturing, stuff of that nature, sometimes cutting. And so while you can certainly use XY2100 controllers for other types of applications, the software for these devices is really optimized for the laser processing of materials, and the features that are included in the software really reflect that. So let's move on to system monitoring. Check off another item on your list. We've chosen a system. We know how we're going to integrate it. We've determined how we are going to command the spicy light. And at this point, we're going to talk about keeping an eye on the system as you're using it. Make sure stuff doesn't break along the way. I try to keep the process of monitoring the health of the system as basic as possible to keep it as easy as possible, because you're more likely to do it if it's easy. And the first way that we can monitor system health is via the diagnostic outputs that are located on the servo amplifier boards. The location on the servo amplifiers means that they are a bit easier to access in open frame systems, where you can have the servo amplifiers affixed to a heatsink just on your benchtop setup. Although we do have some packaged systems that come with these connections to make it a little bit easier to monitor them. Just depends on which one you're getting. Makes it a little bit painless as possible. There are a variety of diagnostic outputs. You can refer to the manuals that we have to figure out which ones are there. But I want to focus on the two that are my favorites for this purpose, and that is the position and the current. The position is the scaled instantaneous output from the Galvo motor. It's buffered through the servo amplifier, and it just tells you where is the Galvo actually in space. And then the second is going to be the current that's drawn by the coil. The nature of servo amplifier design is that the system is always going to attempt to draw as much current as it needs to execute any commands that you've put into the system. Aggressive waveforms, high frequencies, can result in increased current draw, which can result in increased temperature. And that leads to the second favorite method for system monitoring, which is temperature monitoring or thermal monitoring. This does not have to be a high-tech solution. Doesn't have to be ultra precise. You can get a resistance thermistor for under $5. Shout out to the Thorlabs TH10K. Love that thing. You can fix it to your servo amplifier, the mounting bracket, right where the mounting bracket meets the heatsink, and then just keep an eye on it. You can get an idea for how much the temperature changes if you're going through your when you're using the system under your operating parameters, and then get an idea for the overall normal behavior of the system. And then if you notice a sharp increase in the temperature, or if you see the temperature start to creep up towards the recommended maximum, you can just turn the whole thing off. Take a step back. Make sure that everything in your system is good with all of your other system components. Make sure your power supply is in good shape. Make sure your connections are still good. Adjust your thermal management techniques. You can add more heat sinking. You can put in a fan, or I'm sorry, for being fancy, an active cooling system, whatever you want to call it. Monitoring temperature will hopefully allow you to catch these sorts of changes before it results in hardware damage. So I love thermal monitoring, and it's just something that I always recommend for when you're first getting used to a product and you're trying to just understand how it's going to behave under your use parameters. I unfortunately don't have an example of thermal monitoring that we can review, but I wanted to take a moment to just go through the image that is on this slide and just break it down a little bit. This is a screenshot that was taken when operating a QS20X-AG Galvo with a 50-50 triangle wave at an amplitude of 1.3 volts and a frequency of 100 hertz. So in this picture, you can see there are just three basic lines. The orange line is the command that I was sending to the servo amplifier. So this is me telling the servo amplifier what to do. This is where I want you to go. The green line that is slightly behind it is the actual position output that's coming off of that diagnostic output on the servo amplifier. And you can see there's just a little bit of a lag between those two lines. Some of that is just normal system lag. It will always take time for signals to move through a system, but this is somewhat exaggerated, a little bit deliberately, so that you can see them as, two distinct signals, and it's a little bit easier to read. You can see that as the waveform goes along, the triangles are nice and fairly even. The command matches that green line, the position output, pretty neatly. um, and so the system is pretty happy. It's just cruising right along. By monitoring these signals, you can see if the position starts to become unstable, or you start to be able to, or if you've increased the frequency enough to the point where the position is no longer able to achieve the commanded scan angle before it changes direction, in which case you may need to adjust the commands that you're sending. Or you can potentially observe instabilities in the position that say maybe you want to adjust your frequencies, or maybe if this is you're happy with the frequency and everything else performs well, but maybe you just don't want to collect data during that particular portion of the system movement. So that's particularly helpful in the imaging application. So observing just the position output is super helpful. You can keep an eye out for all sorts of various behaviors and adjust your system to really optimize your waves as much as possible. The last line that's in here is the blue line, and this blue line that goes along fairly evenly with its peaks, and this is the amount of current that's being drawn by the Galvo coil. So this is the amount of current that the system's drawing. And you can say that it does remain relatively low and constant as it just kind of cruises right along. But you can see at the corresponding corners where the Galvo would have to change direction that it's going, that there's these sharp peaks of current draw. So this is the point where the servo had to draw additional power resources to slow down the system make the corner, and then speed back up again as it continued on its excursion. The individual peaks of the current are high, and that's fine. But if averaged out, the overall RMS value of the current draw is still quite low. So that's what's important. Individual peaks fine, overall low current draw, that's really what you want. And then in some cases, continuous monitoring of the system is desirable. If that is your system, I would suggest starting with these outputs just to get a feel for them. In other situations where the use of the system is going to be consistent and stable, you're going to be executing the same waveforms over and over again, or it's always going to be operated underneath the same set of parameters each time the system is run. These outputs might just be important tools for learning the limits of your system during the qualification process, and I would strongly, strongly encourage that you use them in that fashion. And that brings us to our very last topic. Um, Again, back to the checklist. We've determined the goals of our application. We've set our priorities. We know what level of integration we're going to take on. We've decided how to not set a mirror lightly on fire. And we know what commands we're going to be sending through the system, and we know how to keep a watch on the system to make sure that it is doing what we want it to do. So now we have to do the final part of the process, which we actually have to pick a system to buy. And a former colleague of mine once referred to comparing Galvos specifications between manufacturers as comparing apples to dump trucks. And oh boy, he was not wrong. Well, I am not capable of forcing an entire industry to standardize methods for specification. I can provide a little bit of insight into how those specifications are defined and at least provide you with the information that I get asked about most frequently so that you know what we're looking at when we take a look at those. So I'm going to start with scan angles. Depending on where you look, some manufacturers specify galvanometer ranges in mechanical scan angles, while some use optical scan angles. Mechanical angles are exactly what they sound like. It is the actual rotation angle of the mirror. The optical scan angle is the angle of the deflected laser beam as it exits the system relative to the center position of the optic. So optical angles are always going to be twice their mechanical counterpoints. In addition to calling out angles as being mechanical versus optical, it's important when looking at a spec sheet or when you're asking for clarification on specifications. You've got to note if the angle that you're looking at is a plus minus range or a total field of view. A galvo with a range of plus minus 20 degrees, optical has the same excursion as an angle with a total range of 40 degrees optical. That plus minus symbol definitely matters. If you're asking a question about specifications and you already know what scan angle you're looking for, and you just want to ask some questions about that, or if you want to ask questions about something in relation to your Galvo system, if you can communicate the scan angles, whatever way you're using, mechanical, optical, plus minus, or total field of view, just let us know which ones you're using, and it'll hasten the conversation and save everybody an extra email or two. The next specification is the one that I would say I probably have to explain the most frequently and that there is the largest amount of confusion surrounding, and that is the small angle step response time. This is frequently interpreted to be the amount of time it takes a Galvo to move the angle that is specified on the datasheet, which does vary between manufacturers, of course. And that's actually incorrect. So this is not the amount of time it takes to make the movement, but rather the amount of time it takes the Galvo to stop moving once it has arrived at its new location. This is also sometimes called the settling time on a spec sheet. So small angle, step response, and settling time are generally the same. And the challenge when looking at this specification is that different manufacturers use different metrics for what they consider to be a settled Galvo. Sometimes it's 90%, sometimes it's 99% settled. What's important is to not get hung up on any individual number, because while this metric can be a good indicator of generic system performance and overall speed, it may not be a relevant value for your particular application. And the last spec that I'm going to cover is going to be linearity, or as it's sometimes called, nonlinearity. As you would surmise, these are two sides of the exact same coin. And the system that is 99% linear will be 1% nonlinear, and vice versa. And while the overall number is straightforward, what makes this specification somewhat difficult to interpret is the size of the field that's being considered for the measurement. Sometimes this is the full field, which is my personal preference, as because it's just the easiest. But it can sometimes be specified as a percentage of the total field, worded as 50% of full travel, or within a range of plus minus a certain number of degrees, or something similar like that. This will matter somewhat less to you if your application uses a small portion of this total scan field, as long as you know if it falls within that portion where the linearity is specified for. But if your intention is to use the full range and your application is one where linearity is critically important, pay attention to how it's listed. Just be aware of what's on the sheet. And the final note that I have about understanding specifications is you can always call us and we will be happy to review any specifications that you have a question about. But if you're ever in a position where you're having difficulty comparing the apples to the dump trucks, if you have a set of operating conditions that you know you're going to be using your Galvo system under, call us up, send us an email, tie it to the leg of a carrier pigeon, whatever you want to do, however you want to communicate. Send us over your waveform information. Say, I want to run this custom waveform at this frequency, at this scan angle, whatever, however you want to specify it. And we'll perform those tests for you. We have a great lab here. I have fantastic colleagues who are wonderful about testing stuff for us. And we'll let you know if our systems are going to function in a way that is going to work for you and is going to work for your application. I love it when that happens. That's great. Sometimes that's not the way things go. We're not always going to be the best fit for every application, and that's okay. So anytime you have a question like that, don't hesitate to pick up the phone and talk to me, or you'll potentially get Corey or another member of our lovely support team over here at Thorlabs. We'd be happy to have a conversation with you about it. And that is all I have for you guys today. Thank you, everyone, for coming and listening to me. I hope I didn't put too many of you to sleep. And if there's any questions, I'd be happy to answer them.
Yeah, thank you, Carol, for the presentation. That was excellent. We do have some questions that people have asked already, and feel free while I'm answering these questions or fielding them to Carol. Feel free to keep sending in questions. We might not get to all of them, but we will follow you up with an email. Probably me or myself or Carol will probably be following you up, answering any further inquiries that you have. So let me get started here. Okay, so I have one here.
Pardon me.
I'm considering using a DAC for analog control for my Galvo. What types of things should I consider when selecting a DAC to control my Galvo?
Ooh, good question, because there's a ton of them out there on the market. And I did touch on this a little bit. So definitely pay attention to the command voltage range. If the DAC outputs in a range, so in a range that is different than the Galvo that you are looking for, either just be aware of that so that you can compensate for that when you are structuring your commands, or if you wanted to give us a call and ask us to tune a system with a different command voltage, that's something that could potentially be an alternative also. The other thing that you'll want to be aware of is make sure that your chosen device can operate in a high Z mode. So high Z versus the 50K mode, anything operated in high Z mode will more closely resemble your actual outputs, whereas a 50 ohm mode won't. So make sure you get something that can operate in high Z. That's super important. And then also keep an eye out for your sampling rate. So I hate to give you a number here that is inaccurate, so I'm going to just like hold my tongue so that it's not immortalized in video. But whatever that like kilosamples per second rate is, figure out what it is for the device that you're looking for, and grab that, and then just give us a call and say, hey, do you think that this is adequate? um, we generally hesitate to advise on specific equipment that people should purchase. And my standard device is, if you have a system that you are already comfortable and confident using, go with that one because it's going to make your life easier. But we're also always happy to even just go over a data sheet with you and see what you're working with, and we can just have a conversation about it. So that's my DAC advice.
Cool. Thank you, Carol. It's good DAC advice. Um, so let's go to a next one here. So I actually have, so there's two people that kind of ask similar questions here, and I'm gonna
Okay.
do my best to lump them together. So I'm gonna read them both here. So
Yep.
the first was, if I wanted to do a custom mirror shape, substrate, or coating, um, how can I go about doing that beyond the stock options that are available? And then the second question that was similar was, is it possible to use other optical surfaces such as half reflective optics or polarizers within the Galvo? So similar types of questions. What can we put on a Galvo besides the stock mirrors that we have?
Yeah. Oh, these are really good questions. So we get asked about custom optics a lot, a lot, a lot. Um, my boilerplate canned answer for this, the quick response is, we can mount just about any sort of a balanced load onto a Galvo system. So as long as it is small enough or has a low enough inertial load that the motor can still move it without damaging that internal rotor, we can probably mount it on a Galvo as long as it's balanced. There are certainly some things that you have to consider when looking at custom optics, beyond just the inertial load. The overall thickness of the optic is super, super important. If an optic is exceptionally thin, then when it's being moved at Galvo speeds, it will twist. And so a certain amount of thickness is required in order to maintain that torsional rigidity so that you don't get that twisting. If it gets too thin, then when you're moving it at Galvo speeds, then that twisting can actually be enough to just snap the optic. Again, fantastic mirror damage. Got pictures of that one too. Again, you know who you are. So as far as mounting something that's a custom shape, or something that's kind of outside of like the standard mirror offerings, like, yes, we can do it as long as it's a balanced load. keep an eye on your inertia. Um, there are specifications on our data sheets that tell you, what like the recommended and the maximum loads for certain ones are. Um, and we're happy to have that conversation with you. We do custom optics on systems quite a bit. Some of them are really weird. Some of them are custom designed entirely, and some of them are just, slightly different coatings than what's currently available. Which also leads me to the secret menu. So, which for everybody watching, Corey's the guy who named it the secret menu. So, so Corey's
Yeah.
secret menu, Corey's super secret menu.
Well, it's more
Um,
Carol's super secret menu, honestly. She has a large, large catalog of custom coatings that they have done successfully in the past. So, as she
I
said, if you
do.
need a certain coating and you don't see it on the website, do not hesitate to reach out and ask about it because the answer is almost always yes, we can do that for these types of galvos.
Yeah,
And maybe I
absolutely.
shouldn't say
The
almost always.
yeah. the the caveat to the caveat to custom optics is, because there's always an asterisk, right? Um, is that while we can probably find just about anything that you're looking for, there's a matter of cost and lead time. That's always something that you'll just want to consider. If you're talking about a single optic in a very low quantity of, 1, 2, 4, whatever, that optic's going to be very expensive. And if this is an exceptionally exotic coating or material, or you have a really bizarre shape that you have to have it fit within, it's going to have a significant lead time. So custom optics are not quick turn, particularly the ones that are designed for Galvo systems, because they do have a fairly unique geometry. And so it's important that if you think that you might end up in a position where you're going to need a non-standard configuration or a non-standard optic on your system, or something that you don't see in the catalog, um, let us know well in advance. Give yourself like a healthy leeway, give yourself a nice runway in order to make sure that you get your parts on time. So that's my asterisk.
Good asterisk. Uh, let's see. I have a good one here. I keep saying that, but I think there are a lot of good questions here.
There's
So
no such thing as bad questions, Corey.
that's what I've been told. Okay, so what would be the aging slash wear that would happen with a Galvo? Would you be able to see some change in performance over time? And if that does happen, what kind of time scale or number of cycles, like what would contribute to premature expiration of one of these Galvos?
Yeah, that's an awesome question. So it's also, I say it's an awesome question because it's one that I have a really hard time answering. So they are they are mechanical systems, and so they are always going to be subject to some amount of wear, just by the nature of existing. Um, the parts inside the systems that are going to be most subject to the wear are going to be the bearings that are built into the motors themselves. So the bearings are going to be subject to wear. They are really high quality materials that we use. Most galva manufacturers use fairly high quality materials for their bearings. But that's really what's going to wear first. And how it wears is entirely dependent on how the system is being used. Exceptionally high frequency, long duty cycles, those are going to wear faster than a system that only operates for a brief period of time or at a low frequency. So it's, I wish I had a better answer for how a system is going to wear, but it's not one that can easily be calculated, unfortunately, because it does vary so intensively between like use case to use case. And then also there's the environmental factors too. A system that is, you know, being operated in a machine shop where there's oil or particulates in the air, is more likely to become contaminated inside the bearings with with external sources than something that's being operated in that sterile lab environment that I talked about earlier. So that's an awesome question. I wish I had a better answer for you. Um, Other than just mechanical wear of the Galvos, I mean, a lot of it's going to be kind of basic sort of best practices for lab environments. Don't touch the boards with staticky hands. Keep the optics in a as humidity controlled or climate controlled environment as you can, especially if they're one of the metallic metallic coated mirrors, like the broad metallic coatings that are subject to becoming tarnished, like I'm thinking specifically of silver, which is really common because it's inexpensive and really reflective at most of the wavelengths. But yeah, if it's in a humid environment, it's not going to behave pleasantly. So behind the mechanical wear, I would say the optics are probably the first thing that would be more.
Yeah,
I would even say that the optics are probably the thing that's going to fail first before the mechanical system wears.
cool. Yeah. Typically, from as I'm on the support end of things, and I have seen, I think, one instance where the Galvo stopped working. And I've seen tens of instances where people have damaged the mirrors. So it's much more common that they don't reach their full lifetime because the mirrors get damaged first because it's
I
a
keep
lack
a
of
whole photo
attention.
album full of
Yes, I
damaged mirrors because they're funny. not not funny when it happens to
not
you,
funny when it happens.
but but funny when
In
it happens to
hindsight,
somebody else. And in
yeah,
hindsight, yeah, it's definitely one of those stories that like is super funny next week, but right now it's
next
not.
year, yeah. All right,
Next
so
year, this is hilarious.
let's see here. I got it. Yeah, let's go to the next question here. So I'm going to rephrase this question a little bit, but I think it's another good one. How do you deal with the heat problem in scanning? Galvos will obviously generate a lot of heat because you're moving a load quickly, you're running current through a coil. This is me ad-libbing this part. Running
Fair enough.
current through a coil to generate your magnetic field to turn the mirror quickly. How do you mitigate this of the Galvo body itself, and what are some things that contribute to rapid heating of your Galvo?
Yeah, so rapid heating, I'm going to kind of answer this sort of in reverse order, and we'll hit a couple points along the way. So rapid heating is typically the result of those two things that I mentioned before, which is high frequency or aggressive waveforms. So things like sawtooth waves, like a true sawtooth wave where there's no kind of structured time component built into the flyback of the command, or really high frequencies. It starts to get hot inside the Galvo body. Unfortunately, there's not a great way to monitor the internal temperature of the rotor, so you are somewhat constrained by your ability to monitor the external stator body. So if you imagine the motor, the shaft of the rotor itself, um, keeping an eye on the temperature at that point and understanding that whatever temperature you're monitoring on the outside, it is probably significantly more intense on the inside of that rotor. So it's going to be warmer on the inside than it is on the outside. And the limitations at that point are going to be the heat sinking that you have in the system for a non-aggressive waveform or a moderate frequency, even some high frequencies, a standard like aluminum mounting system is going to be sufficient to kind of passively cool that rotor and get that heat out of the Galvo body. But for systems where you need to accelerate that process, maybe you build a heat sink into whatever mounting you're using for the Galvo body itself. So whatever you're using to hold that motor in the system, maybe you build some heat sinking into that. And that's also going to be super application dependent, and in each individual system is going to be a little bit different in how they handle that. And you can implement all sorts of different strategies from, you know, a standard sort of just aluminum heat sink, maybe with fans or or fins built into the structure to kind of just increase the surface area that has access to a cooler air environment, or you can go all the way to the extreme, and you can put, you know, some sort of a liquid cooling, like a thermoelectric chiller or something that's running over that system. But don't put the Galvos in water. That's a bad plan. That lets the smoke out. Don't do that. But those are probably the best. That's the best advice that I can really offer as far as thermal management. And I will say that typically the motors themselves are not what gets hot first. The servo amplifiers get hot first. I am not saying that the motors don't get hot. They definitely do. Just the servos get hot first. So if you notice your servos getting hot, use that as a clue to just kind of take a quick peek at your motors and make sure your motors are also doing okay. And if they're not, you know, we can have that conversation about thermal management in your system. Yeah.
Cool. Good answer.
Was it?
Um, yeah, it was.
High five.
Monitor. This is, I will double down with Carol and offer my advice here and say, please monitor your diagnostic outputs when you're using Galvos. It's so much good information and it will save you a lot of mystery and headache in your usage. So please. Um, okay. So this is more of an open-ended, uh, maybe open-ended, but have you heard of applications where Galvos are used for slow adjustments to compensate beam steering, maybe some long-term drift on the order of minutes, seconds, hours, something like that? Or they typically, or are the applications you're more familiar with, or you hear most about rastering, scanning, marking, that kind of thing?
Yeah. So I have to say, and I think I may have said it earlier, that there is no such thing as a standard application when it comes to these systems. There's no such thing as a standard integration. One of the reasons that I love my job is that I get to talk to people who are doing really interesting things using the components that we make. We make these components and we put them out in the world, and then folks find all sorts of banana pants ways to use them. So if you can imagine it, yeah, try it out. Let me know how it goes.
I
um,
think I'm
Give me a call. We'll
guessing,
chat about it. um,
Carol, I
Sorry, go
think
ahead,
this
Corey.
is probably analogous to like closed loop piezo systems for steering, where you will feed
Oh,
some sort of feedback signal. This is what I'm guessing at least,
yeah,
to your Galvo, and it will compensate for some sort of offset via some closed loop, as a piezo would do with a mirror. But
yeah.
I
So,
agree
so
with you.
the
If you can dream it, you can make it happen because this
yeah,
just runs on
absolutely.
analog signals. So,
Yeah. So, so these Galvos systems, these are not open loop systems. These are closed loop systems. So they do already have a positional feedback within the servo loop to compensate for some of that. So if you're talking about just using the Galvo independently for beam steering and then attempting to compensate for any sort of drift over time, you can certainly try and do more than the system is already doing itself, but the systems are generally already set to function in that way.
okay.
I hope that answers the question that was asked. If not, send us an email.
Yeah.
We'll chat about it.
I think we have time for one more question. So
Okay, yeah.
uh, let me get a, let me get a decent one here for to close us out.
Oh,
Um,
see, now everybody whose question you didn't pick thinks that their question isn't decent. So
well,
mean.
they will get special follow-ups with us, so
They
they
will
will
get
have
special follow-ups from us,
more
yes.
attention. So this one's a good one to end on because it's kind of a, yeah, it's kind of a straightforward one. So is there a limit on pulse duration? Would these galvos work with femtosecond pulses?
Ooh, so at that point, you're not talking about a property of the Galvo, you're talking about a property of the mirror.
Hmm.
So that's the optics. So this goes back to sort of the question or the topic when we were talking about the fantastic damage. And that's just pairing the right optic with your particular light source. So femtosecond lasers are special. Um, Unlike continuous wave lasers and nanosecond pulse lasers, which have predictable damage mechanisms, femtosecond pulses have a tendency to, the damage mechanism that they induce is something called avalanche ionization. And that's where I'm probably going to explain this badly. Physicists don't come for me, but the pulses are moving so quickly that as those pulses kind of crash into the optical surface, it can result in an ionization of that surface where it will essentially turn to a plasma. So super cool, science is fun, but bad for your optics. And unfortunately, because this is really happening at like a molecular and an atomic level, it's difficult to predict how that's going to happen. I can tell you without a doubt that I know for a solid fact that none of the optics that I mount on my Galvos are specifically rated for femtosecond pulses. So does that mean that they will not perform using or adequately with a femtosecond pulse laser? No. Does that mean that they will last just as long as they would with a nanosecond pulse laser? No. It really does mean I have no idea how this optic is going to perform. Um, there is, of course, always an opportunity for us to send something out and get something tested underneath specific circumstances or parameters, or for us to source an optic that is specifically rated for femtosecond pulses. But then we start getting back into the conversations about lead times and about the cost of the optics, and you have to kind of weigh that for yourself. Unfortunately, I can't make that choice for you. So yeah, femtosecond pulses, yeah, light gets weird when you wiggle it that fast. That's all I got.
Good answer. Uh, yeah. Okay. Well, that is, I guess, good timing. Thank you for the answer, Carol.
I'm gonna call it.
Um, that is, of course, the end of the presentation. And there are a few questions that we didn't quite get to, so Carol and I will probably be following you up with those via email from us. So look for those if you submitted a question and didn't hear an answer to it. So of course, I'd like to thank Carol once again for her time and the presentation. It's very informative. And
Thank you.
I want to also tease our next webinar, which is up here on the screen. On August 14th, one of our solutions engineers, Eric, will explore some of our quantum technologies. You can register for any of our upcoming webinars on our website at thorlabs.com/webinars. And you will see a view that looks very much like the one that Carol is looking at here. Thank you very much for your attendance, and we hope to see you again. Our host from Photonics Media, Joanna, will close us out for today.
Yes, thank you both so much. That was wonderful. And I just want to let the audience know if they did want to request a copy of today's slides, they can let us know by emailing webinar@photonics.com, and that's webinar@photonics.com, and we will follow up with you. And just so everyone is aware, this whole session was recorded, and you will receive a link to that recording by email. That should go out tomorrow. So finally, I'd just like to thank everyone in the audience today and thank Carol and Corey one last time for presenting. That was wonderful. So this presentation was hosted by Thorlabs and hosted by Photonics Media. So thank you everybody and have a nice day.
Thank you, everyone.
Thank you.